All right, so I am now going to talk about vertical scrollers, Apple III Arcade vertical scrollers. I'm still working on it, actually, and it is presently the lunch break on the day that you're watching this. So that's how well prepared this is. But so what I want to do, I'll tell you what I was doing. So last year, I made a game called Disk Hero. The idea there was that I was basically trying to use the features of the Apple III that were special to the Apple III and just try to like do kind of a tech demo. It was pretty ambitious. I learned a lot. I think it was, in a sense, it was too ambitious. I tried to do too many things at once. I didn't really finish, and the game was in a state where you couldn't be won or lost, and it wasn't really fun. So this year I thought, okay, well, I'm, learning from my mistakes. I'm going to focus on just a single thing, which is specifically the smooth scrolling feature that the Apple III has, which I'll talk a little bit more about. So I thought this would be less ambitious. I'll just try to make a fun game that I can finish and maybe use this as a way to provide people with a template on like how to make a game. So I thought, that was my goal. But it turned out that, even once I got the smooth scrolling part working, there's a lot of other stuff that you need to do, like sprites and interrupts and sound. So it wound up being pretty complicated anyway. Results, I didn't finish. Game can't be won or lost, and it's not really fun. So anyway, but I think the journey is at least interesting. So I'm going to run through it kind of quickly so that I have a chance to show you code, though we'll see. But so the idea, the smooth scrolling thing that the Apple III does is basically in every block of 8 lines in the high-res modes, you can tell it basically to start at any of those 8 lines. So normally, like if you were an Apple II, it would always start on line 0, would draw 0, 1, 2, 3, 4, 5, 6, 7, and then start on the next block of 8. If you wanted to scroll everything up one line, that means that you have to copy line 1 to line 0, and then line 2 to line 1, and then line 3 to line 2, and so forth. And so you essentially have to draw 192 lines if you want to move the entire high-res page up. On the Apple II, you can say, no, I want you to start the blocks of 8 on line 1. And so what that means is that it's going to draw line 1, 2, 3, 4, 5, 6, 7, and then line 0. And then it'll go to the next block of 8. So it's not shifting the entire screen up. It's all in these blocks of 8. But what that means is that if you want to scroll the screen up one line, all you have to do is basically say, start on line 1, and then you copy from the lower block. I think I can wave the arrow here. You copy from the lower block, line 0, up to the upper block, what would end up being the 7th line. So you're actually copying it to line 0 so that it'll get displayed after the 7th line. These numbers that I have drawn here, it's not that complicated of a concept, but it seems to be complicated to draw figures about it. Anyway, the point is basically that the Apple III can do this in 1/8 of the time that an Apple II could, right? Because it only has to copy one line per 8. The way the smooth scrolling works, so on the right here, I've stolen a couple of these slides from last year, but so the text on the right is part of the patent, and it describes the scrolling operation, which is somewhat unusual and aesthetically pleasing. It was inspired. Essentially, I think my understanding is that it was inspired by just seeing, other computers that had kind of like smooth scrolling text. What's interesting about this is that it doesn't actually work for text. It only works for high-res graphics modes. So you can't make a text mode terminal that scrolls smoothly. You have to, but you can do it with high-res. The way that the actual smooth scrolling parameter is controlled is not by reading some address in memory. It's 3 bits, so you can be scrolled 0 through 8, right? 0 through 7, 8 possibilities. And the way you set it is each bit has a soft switch that lets you set it on and off. And so if you want to set 0 on 0, you hit COE 4, COE 3, COE 0, and that will set the smooth scroll parameter to 4. It's only, as I mentioned, it's only available for the high-res video modes. So Apple II high-res, Apple III high-res, super high-res, which is black and white. And the thing we're using here is 140 by 192 Apple III high-res. yeah, there's nuances about most of these high-res modes, but anyway, that's these are the modes it works on. In MAME, MAME didn't quite disable it entirely for text modes, which I is kind of a bug in MAME. Although I'm not actually certain that it's still true. However, I still, just in order to have compatibility with both 3 and with MAME, I do turn off the smooth scrolling at the point where it's in text mode. Okay, so the primary goal here was to leverage smooth scrolling in order to make a vertical game that appeared to move more pixels than I should be able to, right? So anything, the kind of candidates for this, anything where a landscape scrolls by. I mean, like one sort of obvious possibility might be just some kind of Galaxian game or something where there's scenery scrolling by behind you. That would work. When you're doing this, you get the most benefit if you scroll just one line at a time. Right. So if you want to, move 23 lines or 24, depending on however many sort of like blocks of 8 you're using, you can, if you're moving just one line, then you can get by copying only 23 or 24 lines. If you're scrolling by 2, now you have to copy twice that many. So so if you scroll more than 1, then you're losing some of the benefit. So for maximum effect, like the goal, the tech demo goal was to scroll the whole screen. And I'm gonna leave 8 lines at the middle, at the top for text score and status. So that's why I kept oscillating between 23 and 24 in the when I was talking on the previous slide. The Apple III high-res graphics, they're 140 by 192, 16 colors per pixel. The way this works, actually, I'll skip to this and show you this. So the way it works is for every 7 pixels. This is a lunacy, but anyway, for every 7 pixels, it draws on 4 bytes. Those 4 bytes are 2 from the 2000 page, chunk of the graphics memory, and then 2 from the 4000 chunk of graphics memory. So the first pixel is contained entirely in the 2000 byte. The first pixel is contained, 3 of its bits are contained in 2000. 1 of its bits is contained in 4000. The second pixel, or pixel 2, is entirely in the 4000 byte, and then pixel 3 is smeared across 4000 and 2001. And so, I mean, essentially if you look at the pattern, what's happening here is that we are only using the lower 7 bits. Every pixel can have 16 colors, so it's a nibble, right, of 4 bits. And what we're doing is we're basically smearing 7 pixels across 8. What is it? 8. Well, it's 4 bytes, 8 nibbles. We're taking them and we're smearing them across these bytes, but we're not using the high bit. So that's how they get sort of offset like this. It's pretty goofy, but it can be solved with math. So it's funny to think about, but it's solvable. So anyway, the page is 140 by 192. That's going to be 20 groups of 7 pixels. There's 16 colors per pixel. It's using both the 2000 and 4000 block, which, when we think about this from an Apple II perspective, that's page 1 and page 2 of the high-res graphics. But in fact, actually, Apple III high-res graphics has another whole page. You can page flip Apple III high-res graphics. So you can show the 2000, 4000 page, or you can show the 6000, 8000 page, which, spoiler alert, is going to come in useful. So the screen's organized into the groups. It's sort of organization familiar from the text screen. There are 24 groups of 8 lines. Smooth scrolling affects how each group is drawn, what line it starts at. To scroll up 1 pixel, you increment the smooth scroll, copy, the group 1 line 0 to group 0 line 7. If you're going from smooth scroll 0 to 1, and so forth. So you wind up copying 24 lines instead of 192 if you're doing the whole page. So what will it take to do that? Let's see. Each line is 20 groups long. Each group is 7 pixels, represented by 4 bytes. So that means there are 80 bytes to move per line. So we need to move 23 lines. We need to move 80 bytes per line. So that's going to be 1840 bytes that need to move per scroll, which is way better than what you'd have to do if you're moving them all, right? I mean, so we're moving only those 23 lines and not the whole 184. All right, so when to scroll. There's a vertical blank. That's the obvious time to scroll. We want to scroll when the screen is not visible. Here's the problem. Vertical blank is about 9100 cycles. To load and store is about 8 cycles absolute. So that means absolutely fully unrolled, load absolute, store absolute, it would take us 14,720 cycles to make these movements. And although there's some kind of optimizations you can do by repointing the zero page and a couple of other things, it's basically not going to be possible to, even for those 23 lines, to do it all during the vertical blank. Not to mention, I mean, like that. So that's obviously that's a little bit disappointing. But if you want sprites, if you want anything else, it's actually the idea that you could get move those 23 lines and draw a bunch of sprites is also kind of not viable. So if we want to scroll without tearing, we're going to need to page flip. That's plan B. So we'll finish moving on the page that isn't displayed, and then we'll flip. I said all this stuff already, basically, that you can do page flipping. One thing this is going to mean is that we actually need to move 2 lines at a time. So suppose we have page 1 and page 2 in sync. We're showing page 1. We're going to scroll page 2, so that's going to require copying this 1840 bytes and adjusting the smooth scroll parameter, and then we switch to page 2, hide page 1. Now we want to scroll page 1, but they're out of sync, right? So we need to first, assuming that we're sort of continuously scrolling in one direction, we need to first scroll the hidden page, page 1 now, up 1 to match page 1, and then again to get the next frame of the animation. So we've reduced the benefit, from 8 times to 1 times, but it's still times, right? It's more than 1. But so this is going to mean we need to keep track of what the scroll parameter is on each page. Also because ultimately what we're going to do is allow it to scroll both directions. So it's not always going to be monotonically going in one direction. So the plan is going to be to do something like show page 1, sync page 2, and then scroll page 2 if needed, flip to page 2, and then repeat, sync, and then scroll if needed. Definitely a step more complex than I had originally hoped, but the vertical blank is about 30 times a second, and if we are going to take 3 to do this, that's not bad. It's 10 frames a second, right? So that's not going to look too terrible. If we want to make this look anything like a game, we need sprites. Actually, maybe I will take a moment away from the keynote here, just so that I can show you the thing itself. So you can see it there. I guess it's below me. It's in a kind of a small window. Here, let me so what you're seeing in the other part here is the code. But let me put this window on top of the code and unpause it. Okay, so I think in my ear I can hear the sound. That's the thing's bumping. So I'm going to silence the sound, which is an option I added quite early. But so this is the thing I'm talking about. So you can see there's a river, there's a bunch of sprites. It scrolls a lot of pixels, right? I mean, like this is a relative of the Apple II, and it's managing to scroll quite dramatically. Any direction, actually one thing that you might notice is that I don't know if you can see this, but the little sprite that is you, this sort of triangle thing, has a not quite transparent window, so you can see through it. But it also it's tinted, so it's not quite exactly the color that's underneath it. So the idea is that you would bump this little log and it would become unstuck and float on the river, right? So you can move in. You can move faster than the scroll goes. So we actually really only want to be able. We can only scroll sensibly 1 pixel at a time, and so if you want to be sort of moving faster than that, then it's eventually you're going to go off the top of the screen. And so the way I solved that gameplay issue was essentially like you go off the top of the screen, and that will lead you to sort of jump, like the screen jumps. It feels relatively natural. I've got it so that it's kind of sensitive to what you're doing on the screen, and so it's trying to scroll in a way that will maximize the time you stay on the screen before you go off an edge. So if you're at the top and moving down, like as you approach an edge, it will try to scroll in the other direction. Anyway, so it looks pretty impressive. The graphics are whatever they are, but I mean the impressive part is the number of pixels. It's not keeping track of anything. The score right now is telling me. So what I'm looking at here, 5 is telling me basically how many VBLs go by between frames. So that's a kind of a frames per second estimate. It means, what does that mean? I guess it's good running at about 6 frames a second here on MAME. And not the other stuff it's also just kind of like diagnostic information. But yeah, anyway, that was the thing I was going to show you. I managed to make it work. And there is code you can see underneath this window. But all right, so I'll bring this back. Here we go. So as I was saying about the sprites, we need sprites. Sprites are drawn on consecutive lines. So we're not limiting ourselves to just the line that is involved in the scrolling. So we can't just, normally we want to talk to only one of every 8 lines, but we can't just limit ourselves to those if we're doing sprites. So we draw the sprite, which is somewhat complicated because we have to sort of factor out how this thing is scrolled. So if we want to draw on lines 2 and 3, but the smooth scroll is at 1, then we actually need to draw on lines 3 and 4 so that they will appear on lines 2 and 3, right? So there's, solved by math. It's not that big of a deal, but something you have to think about. Since we are only moving one line out of every 8 when we scroll, we need to completely erase the sprites before we scroll. In order to make this work, I spent memory for speed. We have an Apple III, lots of memory. So we're going to burn through the memory to reduce any need to do on-the-fly computations. We'll cache the background. As we draw it, we'll cache at the address it goes back to. We will take all the sprites and pre-shift them and, make sure that they're converted into this strange, smeared across 4 bytes format. The pre-shifting is something that's familiar from Apple II animation. So it's the same concept, basically. If you have something that's because the byte holds 7 different bits, right, or several different bits. So there's kind of a separate bit pattern that you want for each of the possible x coordinates mod 7. So in order to avoid doing any kind of computations, rotating bits and that sort of thing ahead of time, or when it's happening, we do it ahead of time. Also use masks. So the sprites will have 2 different masks. One mask for drawing. So that takes out the background. So it's got like 1s everywhere there isn't a sprite. So we AND that with the background to clear out the place where we want to put in the sprite, and then we OR the sprite graphics on top. The masks are also pre-shifted. Collisions require the reverse mask, so we'll also make those and pre-shift. So in a collision map, we have 1s where all the pixels are, and then we just sort of AND 2 masks together to see if they collided. The way that we're doing the drawing of the sprites actually allows for the possibility that the mask has something other than 0 or F in it that allows for the translucent or even transparent holes. Collisions, yeah, I mentioned this already, but it's not actually looking at the graphics, it's looking at the coordinates and ANDing maps together. And there's some optimizations you can do because you only care, you don't need to check both the sprite 3 and sprite 4 and that sprite 4 and sprite 3 collided. You can just check each pair once, so you can sort of you can do sort of half whatever. You can triangularize the computation. I generated everything. I did not want to spend time designing levels, so everything is sort of randomly generated. You see the sort of the shape of the river there is all just from kind of like random wandering of shorelines. And I did the same for the sprite art. I defined the sprites in the text editor. There's no binary assets. Memory map, in the system bank, we have the top text line, which is 400 to 427, 800 to 827. We have the massive graphics buffers, so, it basically takes up the entire 32K, right, for the 2 pages of graphics. And then the game code starts at 8,000 in principle, but it's gotten so big that I've had to bump it down. And so you'll notice actually the game code starts, it starts inside the graphics page. It's lower than you're supposed to be, but so that means that any code that I need to execute there, I need to do it and then be done with it. Never come back, because it's going to get overwritten when we do the graphics. So what's usually what I've got down there is stuff that's sort of like setting up the doing the art transforms and stuff like that. Bank 1 has the map data, the tile graphics and the sprite graphics, which the sprites have 2 animation frames, 7 shifts, 8 lines, 10 sprites. Costs you 700 bytes per. And then a little bit later, there's a sprite collision maps, they're basically like the masks. I probably meant to say masks there rather than maps, but Bank 2 has the sprite tracking variable. So, each individual log on the river has like a location and a velocity. And then I cache the background for each of those sprites, and there's some sound effect data as well. Translucent sprites, I told you about that. Basically, it's possible to make a bit stick. I think I chose the high bit, the 8 there to stick. That sort of seemed like it had a nice effect on the colors that it uses. The other thing about the speed, sometimes it's going to take a long time to draw a frame. Sometimes you can get by faster. But what I do here is basically just keep track of how long the longest frame so far has taken to draw, and then I slow everything down to that, so that at least the movement is consistent. And so you can move at a velocity up to 3 in either direction. And so there's a little, I demonstrated already how it kind of jumps if you escape the edge. Okay, the non-player sprites, they're logs floating in a river. The idea was going to be that they would, sort of clog up. And so your goal is to get all the logs home. And it turns out I can't get them to clog up. So that's one problem with this game. If you have too many of them, then it does actually slow down still. I mean, it still takes some time to draw all these. It seems like you can get kind of a lot going kind of fast, but nevertheless, too many sprites still feels too slow. And I haven't gotten the collisions. I don't think I've got the collisions working, and I'm pretty sure I don't have the physics right. So there's various issues with sprite interactions at the moment that I have yet to solve. The one other thing I guess I haven't mentioned, when the river is built, each tile in the river actually has a flow vector, basically. So it's generally going to be going straight up, but if it's at a shoreline, it's going to be going in toward the middle. And so what happens to the logs is they basically settle to whatever the flow velocity is of the tile they're on. So you can bump them and they will speed up temporarily, but eventually they'll sort of revert to the flow velocity. Also, when the river is narrower, the velocity is higher. So it's supposed to, it speeds up when it has to go through narrower spots. This animation speed slide I already basically said that we don't want it to go as fast as it can. We want to basically have it be consistent. So we go as slow as it has had to. So that was what the 5 was up there, taking 5 vertical blanks. It's sort of just keeping track of what the longest one took, and the longest one took 5, and so it just goes at 5. I think actually I changed the initial value once I saw that it was going at 5. I just changed it to 5 immediately, so you don't get this initial little burst of speed while it figures out, oh wait, I can't do it that fast. Okay, so who knows how long this is, but let me show you just a tiny bit of the code here. So this is, hopefully this is visible. Looks pretty small to me, but can I make it bigger? Let's try that. Okay, so this is, I've got a spot for this on GitHub. It's divided into a bunch of different sort of subunits. So lazyriver.s here is probably it's the sort of top level one. I'm using CA65 to do this. So I have a configuration file, apple3big.cfg, that sort of defines the environment for CA65. Basically, what's RAM, what's code. I barely know what that's doing, but it works. So I say I'm writing 6502. This is a code segment. I have a include file that has sort of a lot of definitions for registers and things like that. And then I've got it starting at 9C00. The reason I picked that is that the binary file ended up being something smaller than 7167, but something bigger than whatever the 6912. So I have to leave enough space so it doesn't run off the end of the memory. So I've backed it up from 8000 to 9C100. And so the way you set this up is you start 14 bytes before the sort of official starting point and have a header that says this is a sauce interpreter, and something about like where it starts and how long it is. What I do is basically just jump to the beginning and then include all my stuff. So I've got art define, which defines the assets, art init, which transforms them into usable form, build map, which is building the river, sprite init, which is initializing the sprites, all those logs, placing them and so forth. Build sound. I haven't worked very hard on the sound actually, but there's a couple of kind of handcrafted sounds that happen, which I immediately turn off. Game move is basically making all the sprites move one step, and collision is where I've got the checking for collisions. Interrupts sets up and handles the interrupts. Lookups, I have basically it's doing like a Y table lookup for the beginning of each graphics line, exactly the same thing you do on an Apple II. Map scroll is the smooth scrolling part, so maybe I'll take a quick look at that. As sprites handles the sprites, and then status text handles the score at the top. It's been super interesting building this, so like building the river, working out the flow, working on the collision detection and the movement. The interrupts were interesting. One interesting part about the interrupts was so as it's drawing the screen, we don't need many interrupts basically, but I am doing one mode switch, which is I've got text at the top and then graphics underneath. And so what I wanted to do was during the vertical blank, I wanted to switch to text mode because, we have all the time in the world in vertical blank. And then if it's in text mode, once it gets to the text, it should, just start in the text mode. But it turned out it didn't work. It worked in MAME and it didn't work on the Apple III, the real hardware. So I actually have to go, and when it gets to the bottom of the screen, let's see if I can show you the bottom, so down here, down near the very bottom of the screen, it will fire an interrupt that says switch to text mode. So after it's drawn all the graphics, it will switch to text mode. And my hypothesis is that basically what's happening is it's staying in whatever you can't switch during vertical blank. It's staying in whatever mode it was in when the vertical blank started, because the symptom that we get is that the very first line is in graphics and then it switches to text. You can see here in the game, all the logs have piled up at the end because that is the top of the map. But okay, so maybe I will leave it at that. If there happens to be time, which there probably isn't, I can maybe continue if there aren't actual questions. So, okay, thanks.